Swayam Prabha. Digital India. Educated India.
Now let's say Vs is a step. Goes from maybe 0 to 5 volts. Okay. What does Vc look like? So Vs goes from 0 to 5 volts. What will Vc look like? Vc of 0 is 0. This capacitor has a 0 initial condition. Okay. Well, we have done it without that capacitor C1, right? What is the voltage on the capacitor C? What's the value of Vc just after applying the step? So Vc of, okay, that is before I do anything, it has 0 volts across it. Okay. Now my question is, just after applying the step, what is the value of Vc? Now, previously we said the capacitor voltage cannot jump, okay, in the previous circuit, and then we said that it is 0. So first of all, you have a voltage across this capacitor also, right? So before you apply the step, Vc1 of 0 is 0 and Vc of 0 is also 0. Now if you say that this voltage does not jump at all, then the other voltage will jump. Okay, the same reasoning does not seem to apply. So what is the solution? You understand the issue here. The Vc cannot stay at 0 just after the step. Okay, so what should it be? How would you find out the value? Initially, the charge on these two plates is 0 and any current coming through R, okay, will be finite and it cannot change these things instantaneously. Okay, so any instantaneous change can only come from the charge on this plate going into the charge on that plate. Okay, see, first I said that if you assume that Vc is still 0 after the jump, okay, that means that only a finite current was flowing through it. But then this Vc1, which was 0 initially, will have changed to 5 volts, right? The voltage across this capacitor. So that means that there was infinite current there. So those two cannot be balanced. I mean, if you imagine the KCL equation here, the current through the resistor is finite, the current through this capacitor is finite, and the current through that is infinite. That will simply not balance. Okay. So the only solution is where this Vc changes by some amount, but not the same as Vs. So there is instantaneous change in both Vc and Vc1. Okay. So the infinite current that is actually going there, which is really a charged packet that is going into C1, exactly equals that of C. That's the only way KCL will be satisfied at that node. Okay. Another way to think about it is that this dVs by dt, that is definitely infinite here, right? So that can only be balanced by having an infinite value for this also. That means that Vc has to jump. Okay. Is this clear? Now how much will it jump by? So we already concluded that both the voltage across C1 and C will jump. Okay. So that means that the currents through C1 and C are both infinite at that instant. Okay. Not before, not after, but just at that instant. But the current through R will be finite. Okay. So as far as KCL here is concerned, we have some finite contribution and two infinite ones. So we can completely neglect the resistor. Okay. So essentially, you can solve for a step applied to just this network with the resistor removed. Okay. Maybe you have solved problems of this type where initially the charge on this was 0 and the charge on this is 0. Okay. And clearly, if just after the step, let's say this becomes Vc of, as you know, the notation for this is 0 plus, right? So just after the instant of the step. So the charge on this will be C times Vc of 0 plus. And the charge on this will be C1 times Vc of 0 plus minus Vs. That's the charge on this plate. Okay. And those two have to be equal and opposite. Okay. The sum of those two charges, I mean the charge cannot go anywhere else, right, from these plates. So the sum of those two has to be still equal to 0. So if you equate the sum of this and this to 0, what do you get? Vc of 0 plus Vs C1 by C1 plus C2. Some capacitive divider times the input step. Okay. Now this is good only for calculating the step itself. Okay. After that, of course, the current through R will change the picture and so on. So let's say C is 3 nanofarad and C1 is 2 nanofarad. So what is the step? 2 volts. So this will jump to 2 volts. Okay. After that, what happens? What do you think will happen? What is the final value on C when steady state is reached, when no currents are flowing through the capacitors anymore? What do you think is the final value? 5 volts. Okay. So that you can imagine by no current of flowing means you can open circuit the capacitors. So you have Vs, all of Vs appearing here. Another way to think about it is from the equation, all the derivative terms will go off and Vc will be equal to Vs. Okay. So it will creep up to 5 volts with an exponential. And what will be the time constant? Let's say R is 1 kilo ohm. What is the time constant going to be? 5 microseconds. 5 nanofarads times 1 kilo ohms, which is 5 microseconds. Okay. So it is possible to have discontinuities in capacitor waveforms if you apply steps, and this will happen only if you have a voltage source across a capacitor, okay, or across a series combination of capacitors. In other words, if you have a loop containing only capacitors and voltage sources, it's possible to have jumps, okay, because with any finite current you cannot produce a jump in the voltage across a capacitor. It's only with an infinite current can you do that, okay. If you take a capacitor and apply a voltage across it, clearly that will draw infinite current, and then the capacitor voltage will change to whatever the voltage source is. Similarly, if you have a loop of voltage source and capacitors, the same thing will happen.
We can also evaluate Vc1, the voltage across the capacitor C1.
So it will jump to 3 volts. And what is the final value? 0. So what happens to the waveform? It will do that. And it will also have the time constant, which is 5 microseconds. So just looking at this, I can write that this equation is 3 volts exponential minus t by 5 microseconds. And the equation for this blue stuff would be what? 5 volts minus 3 volts exponential. It's not 5 volts, because if it's 5 volts, it means it starts from 0. Okay, it starts from 2 volts. So it is 5 volts minus 3 volts exponential minus t by 5 microseconds. Okay.